So can you remind me which questions we were doing from 1-5?
2.
2, 4, and 10. So question 2, calculate the following series. So these are plug-in questions. So sum from k equals 1 to 3 of I to the n equals 1, 2, 3, 4. So this one is potentially a typo, but possibly not. So let's just pick the n equals 1 case, okay? So sum from k equals 1 to the 3 of I to the 1. I to the 1 is just I. Sum from k equals 1 to 3 of I. Well, what does that mean? It means set k equal to 1 and evaluate I, set k equal to 2, evaluate I, set k equal to 3, evaluate I, add them together. This is just 3I. Now, if it had said sum from I equals 1 to 3 of I, right, that would be set I equal to 1, I is 1, set I equal to 2, this is 2, set I equal to 3, this is 3, add those together, that would be 6. And usually when you see a sum, there's something to do with this symbol in the expression that you're summing, but doesn't have to be. And so if this was 2, this would be sum of I squared, and that would just be 3 times I squared, and so on. Sum from I equals 1 to 5 of 20 is a good question. So what's that going to be? That's going to be 20 plus 25 times. That's going to be 100. So think for loops, right? For I equals 1 to 5, sum equals sum plus 20, where sum starts off at 0. Sum of, this one looks more interesting. Sum from j equals 0 to 3 of n to the j plus 1. So when it says for n equals 1, 2, 3, 4, it means there's 4 problems to do here, right? So for example, if we set n equal to 2, this is the sum from j equals 0 to 3 of 2 to the j plus 1. So that's 2 to the 0 plus 1 plus 2 to the 1 plus 1. 2 squared plus 1, 2 cubed plus 1. Right, so sum of j equals 0 to 3 of 2 to the j plus 1, just plug in j equals 0, 1, 2, and 3, add up each of those expressions. So this is 2, this is 3, this is 5, this is 9. So there's 19.
So you're just doing 4 different sets for 1 for each?
Yeah, so do it for n equals 1, then do it for n equals 2, and so on. And then sum from k equals minus n to k, and minus n to n of k, and that's just a straightforward sum. But with perhaps an interesting result. So if n equals 4, that's the sum from k equals minus 4 to 4 of k. Alright, and all of that's just going to be a 0. And it doesn't matter what n is, that's always going to end up being a 0. So that's playing around with summations and working with the definition. How about verifying these properties for n equals 3? So let's look at this first one, and the second one is basically the same. So sum from I equals 1 to n of the quantity AI plus BI equals the same thing if we split this into two summations. So we're asked to verify that this is equal to that. So we'll talk more about this soon, but when we're asked to verify that two things are equal, what we really need to do is start with the first thing, and by applying logic and mathematics and reasoning, turn it into the second thing. Okay, if you want to show two things are equal, take the first thing and show that it's equivalent to the second thing. Show by transforming it into things that are still equal to it until you transform it into the second thing. Okay, there's a temptation to take the first thing and the second thing and try to do things to both of them until you get to two things that are equal. That does not work. And I'll show you a really pathological example why that does not work. Prove that 1 equals 2. Well, 1 times 0 equals 2 times 0. 0 equals 0. Yes, 0 does equal 0, so 1 must equal 2. Now that's obviously silly, right? But it is so easy to do this without realizing that that's what's happening when it's something more complex than 1 equals 2. The correct way to do this would be to start with 1 and say this is equal to, I don't know, 0 plus 1, which is equal to, 3 minus 3 plus 1 squared, and keep doing that until eventually you show that it's equal to 2. Well, we can't do that because it's not equal to 2. But if you could, then you would prove it. So we're going to take one of these and try to show that it's the same as this. Let's just pick on this one. So let's take the left-hand side, and I'm going to write it like this. Sum from I equals 1 to n of AI plus BI. And I'm just going to use what the summation means. This means, set I equal to 1, this is A1 plus B1 plus A2 plus B2 plus A3 plus B3. Haven't done anything except apply the definition of this summation symbol. But now I'm going to use what I know about addition and say that this is equal to A1 plus A2 plus A3 plus B1, B2, B3. And my fancy argument to the jury is commutativity of addition. Right? And they'll say, okay, I guess that is equivalent. And now, I'm going to use the definition of summation to say that this is equivalent to that. And this sum of b's is equivalent to that. And now I've shown with nothing up my sleeve that this is equal to this plus this. And now we can say QED, which is Latin for which is what was to be proven, or what we were asked to demonstrate. And it basically says there's your proof. So that's a demonstration that for n equals 3, this is the same as that. And to do this for the case of multiplication is exactly the same thing. Write out that sum using what the sigma means. Multiply each term by c. Now distribute the c, right? And then take each of those individual c's and write that as a separate summation. And you'll see that it's the same thing. And so that's verifying or demonstrating something, but it's a hint of the proofs that we're going to do next week. And then 10 is the same thing, but we're doing products instead of summations. So product from k equals 0 to 3 of 2 to the k. Did anybody do that? Product k equals 0 to 3 of 2 to the k. So set k equal to 0, set k equal to 1, set k equal to 2, set k equal to 3, and just multiply all of these. All right, the other one is particularly interesting. So who got an answer for this one? What did you get?
1 over 101.
1 over 101. And you didn't do 100 multiplications, right? All right. So you explore this, right? This is not a formal proof, but it's an exploration of it. Thinking out loud on paper. If k is 1, this is 1 over 2. If k is 2, it's 2 over 3. If k is 3, it's 3 over 4. If k is 100, it's 100 over 101. And you notice that these terms cancel, right? And the previous term was 99 over 100. So those cancel, and so it's going to end up just being the 1 on top and the 101 on bottom. Now, if we were asked to prove it, that's not a proof. You would need to actually write out all 100 terms and cancel them, because we can't really do this ... and call it rigorous mathematics. But we're going to learn a piece of machinery in a few weeks called mathematical induction, which is basically the way we can formalize this notion of ... When we see something and we know that we could do it if we were patient enough and had enough paper, we'll be able to invoke mathematical induction and show that rigorously we could keep doing this and it would work in all cases. And that's going to be our most powerful mathematical tool this whole course, is mathematical induction. And it's going to feed directly into our data structures course, CSE 222 in winter. So that's kind of a spoiler for the punchline. All right, any other questions?
Can you go over 3.3, number 2, C and D specifically?
Yeah, so I want to talk about implications separately, but let me just give you an idea. Give an example of a proposition other than X that implies X. So X is this weird three-part thing, P and not Q, or R and P. All right, we want an example of a proposition other than X that implies X. So we're looking for something which implies X. Okay, let's just call this S for something. So find an S such that S implies all of this stuff. Or we could think of this as find an S such that if S, then X. Because that's what implication is, right? S implies X. So we're looking for some expression other than this thing itself that if it is true, then we know that this is true. And we always know if X is true, then X is true, right? We always know X implies X. But the question says other than that example. So is there something we can find that if it's true, we know that this whole thing is true? And yeah.
Could we write a truth table and then find out another way to write that equation?
You could write a truth table and find something so that whenever this thing is true, this turns out to be true. There's a bit of an easier way to do this also.
Because there's two statements with an or in between them, you know that if one of the statements is true all the time, then X is also true all the time.
Right. So this is something about the property of this disjunction, this or statement. If, for example, R and P is true, then there's no other possibility except to conclude that this longer thing is also true. Right? Because if this is true, so the or of this with anything else is true. Whether this part is false or true, that ORed with something that's true is going to be true. So if R and P is true, then this thing ORed with R and P is also true. So that's something other than X which implies X. The kind of flip side of that is part D. Give an example of a proposition other than X that's implied by X. So if we know that this is true, what does that imply? Does it tell us something that we know is true given that this is true?
Or that with something else.
Yeah, it definitely implies P and not Q, or R and P, or, I don't know, not R. Could be anything, could be a totally new proposition. If this is true, we know that this thing is true because that part is true and it's being ORed with something. There's also something else that X implies. And this you might get from a truth table. It turns out if X is true, P has got to be true. And if you look at what X is, it's saying that either this expression is true, which means P is true and Q is false, or this expression is true, which means P is true and R is true. In both of those cases, P has to be true. So the only way that X can be true is if P is true plus some other stuff happens. Right? P has to be true and either not Q is true or R is true. You could also find this by factoring out a P. And X is actually P ANDed with this other expression. And if we know that P and this other expression is true, then we know in particular that P is true. So X implies P. That's another answer. So this is digging more into the nature of these implications, these if-then statements, which is what we want to concentrate on today. So if P, then Q, P implies Q. And we already talked about converse, inverse, and contrapositive, right? So what's the converse of if P, then Q? Do you remember? Just flip them around. If Q, then P. The inverse, we just negate. If not P, then not Q. And the contrapositive is both. It's like the converse of the inverse, or the inverse of the converse. If not Q, then not P. All right, we can also make a biconditional, by the way. Which is basically saying if P, then Q, and if Q, then P. If P is true, then Q is true, but also if Q is true, then P is true. And we can say P if and only if Q. That's just a shorter way of saying this. And we can write this as basically a double-headed arrow. And we interpret this as meaning P arrow Q, but also Q arrow P. So we've got both implications. And so P and Q are either both true or both false. So it gets interesting when we look at truth tables. So let's look at P and Q. And let's look at the possibilities. And let's see what the truth value of if P, then Q is. Okay, so fix in our minds, if P is true, then Q is true. That's what this statement on the right says. If P is true, then Q is true. And let's look at our last row of the truth table. Suppose that P is true and Q is true. Then is this if-then statement also true? right? This is absolutely true. If we pick some propositions P and Q, is P true? Yeah. Is Q true? Yeah. Okay, so is it correct to say if P then Q in this case? Yes. Because if P is true and it is, then Q has to be true and Q is true. On the other hand, suppose P is true and Q is actually false. Are we correct to say if P then Q? Right, this is exactly the opposite of reality. We're saying if P is true then Q is true. Well, in this case P is true, but Q is not true. Q is false. So in this case, the implication is false. All right, what about this one? What if P is false and Q is false? And this one is usually a little disturbing, usually very disturbing. Because it turns out if P is false and Q is false, then this if statement is true. It's a true statement to say if P then Q. Why? Because P is false, so Q does not have to be true. This only says if P is true, Q is true. Well, since P is false, this statement is making no claims. And in fact, neither is this one. But this second row is not too hard to believe, because since Q is true, right, Q is true, so if P is true, Q is still going to be true. If Q is false, we're not saying anything about Q. But that first row can be disturbing. And it leads to all kinds of weird things that seem illogical to us. So, let P be the proposition 1 plus 1 equals 3. Let Q be the proposition my name is Izad. So this if-then statement says, if 1 plus 1 equals 3, then my name is Izad. That's a true statement. That conditional statement is logically true. And it's a ridiculous statement, because the laws of mathematics have nothing to do with my name. My name is not Izad, my name is Nick. But from a Boolean algebra propositional logic perspective, this is a true statement. So let me give you a different example of propositions that make this a little more palatable. So let P be the proposition x is bigger than 5. Let Q be the proposition x is bigger than 2. So if P then Q says the following: if x is bigger than 5, then x is bigger than 2. Is that if-then statement a true statement over integers? If an integer is bigger than 5, then it's bigger than 2. Is that true? Is it always true? Right? There's no way to argue with this. This proposition must always be true. The only way it could fail to be true is if we found some integer that was bigger than 5 but not bigger than 2. In other words, if we found some magic value of x for which x was bigger than 5 but it was not bigger than 2, then this if-then statement would be false. Any other case, this statement is true. So what is this first row? This first row is simply the case where x equals 0. Is x bigger than 5? No. Is x bigger than 2? No. That does not invalidate the fact that this statement is always true. And the second row is the case where perhaps x equals 3. So is x bigger than 5? No. Is it bigger than 2? Yes. And in that case, this statement is still true. So these three rows represent all the possible statements we could make for any value of x. This third row is not possible. There is no x that's going to cause P to be true and Q to be false. That's exactly what this if statement is saying. So it can feel a little weird, it might be a little hand-wavy, but we're going to work with this idea that if P then Q has this truth table. It's true in all cases except when P is true and Q is false. All right, so we'll remember that truth table. Put that up here for reference. And we'll repeat if P then Q. And now I want to make a column for if Q then P. And if Q then P is only going to be false when Q is true and P is false. So Q is true and P is false. This is the row where Q implies P is going to fail. And all the other rows it's going to be true. And so now if I take the conjunction of these two, if P then Q and if Q then P, well, true and true is true, true and false is false, false and true is false, true and true is true. And this is what we called our biconditional, P if and only if Q. So what's a biconditional? It's telling us that P and Q are both either false or both either true. They have the same value. So this is why it's an if and only if. P is true if and only if Q is true. So P is true if Q is true and Q is true if P is true. So they're equivalent in some sense. Let me add one more row to this table. Two more rows. So not Q, I'm just going to complement the value of Q. That's true, false, true, false. Maybe I don't want to do that. Brain freeze, hold on. Let's do not P. Okay, so I'm complementing P, that's what we call not P. So let's look at not P or Q. So we want to look at Q and we want to look at not P and see if either of those is true. Well, true and false is true. True and true is true. False and false is false. False and true is true. And the thing to note here is that this column has exactly the same truth values as this column. True, 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 false, false, true, true. So if P then Q is what we can call logically equivalent to not P or Q. So that's our first of many logical equivalences. If you see the statement P arrow Q, if P then Q, you can substitute that with the expression not P or Q, and you haven't changed anything. But sometimes it's easier to work with nots and ors than it is with arrows.
So the phrase logically equivalent means same truth tables.
Same truth tables, yes. Or if you like, it means the truth values are the same in all possible situations. which is what same truth tables tells you. And we find lots of logical equivalences. For example, if we take P and we OR it with not P, we've discussed this is always true, right? It's raining or it's not raining. One of those has to be true. So this is logically equivalent to true. And we can write a logical equivalence with this triple equal sign. And true is just always true, right? So this is saying this expression is always true. We can also write things like P and not P. And that's logically equivalent to false. It's raining and it's not raining. Well, it does that in Vancouver, actually. But today is Friday and today is not Friday. That's a false statement, right? P and not P is always false. And the statement we just saw a moment ago, P implies Q, is logically equivalent to Q or not P. So these expressions that are logically equivalent to true, those have kind of a special place in logic. This is called a tautology. It's something that's always true. And something that's logically equivalent to false, we can call that a fallacy. Or we could call it a contradiction. Let's call it a fallacy for now. These things that are neither logically equivalent to true or false, but are equivalent to something that depends on the values of the variables, those are called contingencies. So most logic expressions are either true, false, or dependent on the values of the variables. Unless you're into weird stuff like the continuum hypothesis.
So a contingency means anything other than a tautology or a contradiction?
Yes. All right, so we have identities. For working with logic symbols. So let me just say, let P, Q, and R be propositions. I'm not saying what propositions they are, but some propositions. So we always know the following things. P ANDed with true is always equal to P. Unknown proposition P and today is Friday, that has the same logical value as whatever proposition P has, because we're ANDing it with something that's true. Today is Friday. P ORed with false is also logically equivalent to P. It's going to rain today, or 1 plus 1 equals 3. Well, that statement is true precisely if it's true that it's going to rain today. P ANDed with false is a fallacy or a contradiction. And P ORed with true is a tautology. The moon is made of green cheese, or 1 plus 1 equals 2. That's a true statement. And P ORed with itself is equivalent to P ANDed with itself, which is equivalent to P. So you recognizing these? Right, we saw these in set theory, we've seen them in 250. The negation of P is logically equivalent to P. And there's fancy names for these. This is called the identity. This is called domination. This is called idempotence. This is called double negation. It always feels like they ran out of creativity when they got to that one. There's commutativity, there's associativity, right? So P or Q is equivalent to Q or P. Same with ANDing. P or Q ORed with R is equivalent to P ORed with the expression Q or R. So that's commutativity. This is associativity. And it works for conjunctions as well as disjunctions. We have distribution. P ORed with Q and R is logically equivalent to P ORed with Q, expression ANDed with P ORed with R. And we can also flip the ORs and ANDs and we get another version of that. P ORed with P and Q is logically equivalent to P. This one's not as obvious, but for this OR to be true, we need either P to be true, which gives us that, or we need P and Q to both be true, which again gives us P. So certainly if the left side is true, we know the right side is true. On the other hand, if the right side is true, if P is true, we know immediately that the left side is true because the left side is true ORed with something. But if we wanted to not wave our fingers and actually prove this, it's not too bad to do. So there's P and Q. Let's put in a column for P ANDed with Q. And now let's take this column and OR it with that column to get P ORed with P and Q. So false ORed with false is false. False ORed with false is false. True ORed with false is true, and true ORed with true is true. And so here again, in every possible case, the truth values of this expression exactly match the truth values of this expression. That's enough to show logical equivalence. Truth tables are the same. So that's absorption. P ANDed with not P is logically false. And P ORed with not P is logically true. And that's called negation. And then everyone's favorite, and then we'll take a break. The negation of P or Q is logically equivalent to the negation of P ANDed with the negation of Q. And the same if you flip around the ands and ors, and that's De Morgan's theorem. There's other identities as well, but these are sort of the big players. And we'll use these again and again. All right, so let's do a 5-minute break, and then let's apply these to proving some theorems about propositions so that we can show equivalence of things without having to use truth tables. And then we'll start talking about predicates and quantifiers, and we're going to talk about weird infinity stuff at the very end.